So as I was saying, the tests aren't graded yet, so I'll have those back to you tomorrow. Looking at our next section of the course, we're going to start talking about exponents a little bit and some of the rules that come along with them. You know, we've seen things like 10 to the third, and of course we know that that means what?
10 times 10 times 10.
Perfect. That means that we have 3 tens multiplied together. 10 times 10 times 10, which gives us 1,000. Now at this point, I'm going to trust that you all know how to enter that into your calculator using the caret key or whatever key your calculator has. But I just want to repeat the parts of the exponent. That whole thing there, 10 to the third power, is an exponent. The 10 is considered the base of that exponent. The 3 is considered the power. So everything we're going to do today, we're going to be talking about exponents with the same base. So if I have like 10 to the fourth times 10 to the third. Many of you probably already know the rule for that. What's that end up being? 10 to the seventh. Good. When we're multiplying exponents with the same base, we add the exponents. 10 to the fourth times 10 to the third is 10 to the 4 plus 3, or 10 to the 7th. If I'm dividing exponents with the same base, what do we get? 10 to the 8th divided by 10 to the 5th. What do we end up with? 10 to the 3rd. Very good. When we divide, the exponents are subtracted. 10 to the 8th divided by 10 to the 5th, we do 8 minus 5 gives us 3, so 10 to the 3rd. The reason for each of those rules, let's look at this one up here. 10 to the 4th times 10 to the 3rd. Well, 10 to the 4th means 4 tens multiplied together. 10 to the 3rd means 3 tens multiplied together. If I'm multiplying both of those together, I now have 1, 2, 3, 4, 5, 6, 7 tens multiplied together. Just adding the exponents together. So even though it looks like we are adding, and mechanically that's what we're doing, it is still multiplying those exponents. Down here for the 10 to the 8th divided by 10 to the 5th. Starting to regret using the power of 8 right now. There we go. It's 8 tens multiplied together. 10 to the 5th is 5 tens multiplied together. And when we reduce a fraction, we can treat division as a fraction. We can cancel out common factors. So as we cancel out those tens, we see that we are left with 3 tens on top, so that's 10 to the 3rd. Of those 8 tens, 5 are canceled out because we're dividing by 10 to the 5th. That's why we can subtract the powers when we divide exponents with the same base. A rule similar to that, a power of a power in our exponent. So 10 to the 3rd to the 4th power, that means there's 4 of those 10 to the 3rds multiplied together. Now I could write this out. There's 3 tens. There's another 3 tens. How many total tens are we going to end up having here? 12. We've got 3 of them 4 times. In fact, that's exactly what we do is we take 10 to the 3 times 4, gives us 10 to the 12th. So when we have a power of a power like that, we can multiply the powers of the exponent. Of course, the same would be true if we have variables as our base. X to the 5th times x to the 12th is going to give us
X to the 60th.
Careful.
Or, yeah.
17th. There we go. When we're multiplying, remember the powers add together. x to the 8th times y to the 5th is going to give us
xy to the 13th.
Got to be careful on that one. Remember, we can only combine the powers if the exponents have the same base. So x to the 8th times x to the 5th is just x to the 8th y to the 5th. Dividing, x to the 9th divided by x to the 4th is going to give us x to the 5th. Y to the 19th divided by y to the 11th. Y to the 8th. Very good. Z to the 5th to the power of 9. Z to the 45th. Very good. And x to the 9th to the power of 11. X to the 99th. So those rules are pretty basic and easy to work with. But what if we combine more than one of each? X to the 3rd, y to the 5th times x to the 8th, y to the 7th. We could do each of them separately. We can multiply the x's. What is x to the 3rd times x to the 8th? X to the 11th, good. Y to the 5th times y to the 7th? Y to the 12th. Now I could have times in between them, but I don't need it. It can just be x to the 11th, y to the 12th. Same is true with the division. I can have x to the 8th, y to the 5th over x to the 3rd, y to the 4th. When I divide that out, what do I get for the x, I should say? To the 5th. 8 minus 3 gives me 5. And for the y?
1.
Just y, right? Y to the 1. 5 minus 4 is 1. So y to the 1 or just y. Well, the same type of concept applies with the powers. If I have x to the 5th, y to the 7th to the power of 4, I can separate those out and do each separately. So x to the 5th to the power of 4 gives us x to the 20th. Y to the 7th to the power of 4? Y to the 28th. Very good. Same even applies if we have the division. I might have x to the 8th divided by y to the 5th to the power of, let's go 5. I can do each piece separately. What is x to the 8th to the power of 5?
X to the 40th.
X to the 40th. And y to the 5th to the power of 5?
25th.
Y to the 25th. So we are multiplying the powers on each. We can keep the fractions separate. Our next step is to look at some special powers. Like x to the power of 0. Anybody want to venture a number, an answer for that?
1.
It is 1. A lot of people would throw out 0. That's the answer I was expecting to get. But it actually is 1. Any number, any variable to the power of 0, anything to the power of 0 is 1. The reason for that, let's go to our tens here. If we had 10 to the power of 4, what does that equal? 10,000, yes. Many of you probably learned a shortcut. Whatever the power is, that's how many zeros end up being in your answer. 10 to the 3rd ends up being 1,000. 10 squared, 100. Now, just like we did with multiplying negatives, we're going to look for a pattern here. When our base of our exponent is 10, we're going to keep that the same. We're going to change the power by 1. So we went from 4 down to 3, 3 down to 2. What would our next one be? 1, right? 10 to the 1. Our result each step is divided by 10. 10,000 divided by 10 is 1,000. 1,000 divided by 10 is 100. So 100 divided by 10, what should this answer be? 10. 10 to the power of 1 is 10. So our pattern holds true. So if we continue it, what would come next? 10 to what power? 0. 1 minus 1 would be 0. What's 10 divided by 10? 1. So 10 to the power of 0 is 1. And I can show that same pattern with any number as the base of that exponent or any variable as the base of that exponent. So anything to the power of 0 is 1. As I've mentioned before, go ahead.
I was just going to ask where using a power of 0 would be used and for what?
It ends up, certain formulas that have powers in extreme circumstances can come out to a power of 0. It does not happen very often. What it is when you have like exponential growth and decay formulas, you might have a formula that the amount of a material is, you start out with 2,000 grams and it decays as a half of it per day, so to the power of x. Well, when x is 0, 1/2 to the power of 0 is 1. So that's saying you started out with the full amount at time equals 0. Which isn't terribly useful, but it's a starting point. It's a transition point. Now, if we keep going with this pattern, 0 minus 1 would be -1. So that'd be 10 to the -1. We would keep going dividing by 10. 1 divided by 10 would be 1/10. Continuing, it would be 10 to the -2. 1/10 divided by 10 is 1/100th. 10 to the -3, 1/100th divided by another 10 would be 1/1000th. And you might notice a pattern developing here with those negative powers as well. 10 to the power of -3 is related to 10 to the power of +3. It's reciprocals. 10 to the power of -3 is just 1 over 10 to the 3rd. And that actually is the definition of a negative power, is it is a reciprocal of its positive power. One of the things that they'll ask us to do in my math lab is to express answers with positive exponents. So you might be given something like x to the 5th, y to the -4th, z to the 7th. And when you're asked to give that to positive exponents, we have to get rid of that y to the -4th. So the x to the 5th doesn't have to change. That y to the -4th becomes 1 over y to the +4th. That z to the 7th is just z to the 7th. It doesn't have to change. Well, to make this a little bit cleaner, instead of having it written out like that, we'll multiply them together. So we make the x to the 5th a fraction, x to the 5th over 1. We'll make the z to the 7th a fraction, z to the 7th over 1. Now if we multiply out on top, x to the 5th times 1 times z to the 7th, that's x to the 5th, z to the 7th. On bottom, 1 times y to the 4th times 1 is just y to the 4th. That's our result right there. Now, some of you may have been taught a shortcut, and it's very valid, to get from this starting point to where we finished here, that negative powers just get moved from numerator to denominator to make them positive. For example, in that case, all I had to do is rewrite this with the y to the -4 gets moved to the denominator, and it becomes positive. That's exactly what we had for our answer. A little bit trickier is what happens when you have 1 over something to a negative power. Well, remember, x to the negative 3 is 1 over x to the third. So this is 1 divided by 1 over x to the third. Now to divide this out, I'm going to have to do division with fractions. I make this a fraction by making it 1 over 1. And then to divide it out, I change it into times the reciprocal. So the reciprocal of 1 over x to the third is x to the third over 1. 1 times x to the third is x to the third. 1 times 1 is 1. X to the third over 1 is just x to the third. So back to our original problem here to explain the shortcut. 1 over x to the third, we said we could move a variable, an exponent, from the numerator to the denominator to make it positive. We can do the opposite as well. We can move it from the denominator up to the numerator to make it positive. So 1 over x to the negative third is x to the positive third over 1, or just x to the third. So we're making a little bit of a leap in level of difficulty here for a second. We're going to do x to the fifth, y to the negative third, over w squared z to the negative fifth. If I want to express this using only positive exponents, only positive powers in my exponents. First of all, which variables, x, y, w, or z, are okay right where they're at? So x to the fifth is going to stay on top. W squared is going to stay on bottom. They're okay just where they're at. It's only the ones with negative powers that need to move. So what's going to end up on top with the x to the fifth?
Are you just swapping the y and the z and making it positive there?
You got it. The z to the negative fifth is on bottom, so to make it positive, we're going to have to move it to the top. Oops, it's not negative anymore, it's positive. Z to the positive fifth. Y to the negative third is negative power. It's in the numerator. To make it positive, we move it down to the denominator. That's now y to the positive third. We should double check, by the way, to make sure our variables are in alphabetical order in both the numerator and denominator. In this case, I set it up so they would be, so we are okay. So in your notes, I want you to try this one. A to the negative fifth, b to the negative third, c to the fifth, over d to the eighth, f to the negative fourth, and g squared. I'll give you about 10 seconds to go through that one. So what do we end up with on top for this?
Do the fifth and f to the fourth?
Okay, c to the fifth stays there. And yes, the f is the negative 4 on bottom. It goes up to the top as x to the positive 4. So what's going to go on bottom? Perfect. Perfect. A to the fifth. It's a to the negative fifth, so we have to move it to the bottom to make it a to the fifth. B to the negative third on top, so we move that to the bottom to make it b to the positive 3. And the d to the eighth and the g squared stay down there. And those are in alphabetical order, so that is the answer. Any questions on that? Let's go ahead.
Okay, will my math lab count it wrong if they're not in alphabetical order?
It shouldn't, but it might. If it does, if it's homework, it's not a big deal. If it's on a quiz, let me know and I will go back in there and I will regrade that for you. So let's now look at the next step. Since we've got our negative powers into the mix here. What is x to the 7th times x to the negative 16th?
X to the 9th.
Careful, you're close. Negative 9th, right? We're adding powers. So 7 plus negative 16 is 7 plus negative 16 is negative 9. Y to the negative 13th times y to the 21st. Y to the 8th. Good. Negative 13 plus 21. Yeah, negative 13, positive 21. That is y to the 8th. X to the negative 7 times x to the negative 12. Perfect. X to the negative 19. It's a little bit trickier when we hit division. X to the negative 8th divided by x to the 7th. Well, that's negative 8. There you go. Negative 8 minus 7 becomes negative 8 plus the negative 7. That is x to the negative 15. Here's another tricky one. Y to the 9th divided by y to the negative 12th. Y to the 21st. Good. That is 9 minus a negative 21, which becomes 9 plus 21. Or sorry, 21. 9 minus a negative 12, which becomes 9 plus a positive 12, which is 21. So y to the 21. What if I have 10 to the negative 9th divided by 10 to the negative 23rd?
Negative 14.
You're close.
10 to the negative 14.
Negative 9 plus 14. I heard somebody whispering it there. It is a positive 14. Yeah. Negative 9 minus a negative 23 becomes negative 9 plus 23, which is positive 14.
So the 10 and the 10 don't divide to make 1 there?
Nope, we don't divide. Remember, it's the same base of our exponent. It won't divide out.
Yeah.
X to the negative 19 divided by x to the negative 13.
X to the negative 6.
There we go. Yeah, negative 19 minus a negative 13 comes negative 19 plus a positive 13. Negative 19 plus 13 is negative 6. So x to the negative 6. What's x to the 5th to the power of 8? X to the 40th. Good. How about y to the 4th to the power of negative 7? Y to the negative 28th. Z to the negative 6th to the power of 9. Z to the negative 54. Good. And x to the negative 7th to the power of negative 5. X to the 35th. Very good. Well, we can make it a little bit worse. Just what you wanted to hear, right?
I think we knew it was coming.
It's kind of what I do. Something like this. Now that fraction bar, it's division, but it's also an enclosing symbol. So it's telling us we have to do everything on top first. So we have to do that x to the 8th times x to the 13th, which is x to the 21st. Very good. Now if there's anything to do on bottom, we would have to do that next. In this case, there is not. It's just x to the 5th. Now we can divide x to the 21st divided by x to the 5th. X to the 16th. Very good. So let's try this one. Once again, we have to do what's on the top of the fraction bar first. Y to the 7th times y to the 9th is y to the 16th. Y to the 12th times y to the 15th is y to the 27th. And if we divide those, y to the 16th divided by y to the 27th, y to the negative 11th. Very good. So, looking at this one, a little bit more interesting. X to the negative 13th times x to the 8th. X to the negative 5, good. X to the 11th times x to the negative 20th. X to the negative 9. And then we divide x to the negative 5th divided by x to the negative 9th. X to the 4th. Perfect. Negative 5 minus a negative 9 is negative 5 plus 9, or 4. So this one's a little bit more interesting. I wrote a little bit small there, but here's our main fraction bar. It's our main enclosing symbol. We have to do everything on top first. Well, we see up on top that there are some other things that we have to do before we get too far. We're going to have to divide out this one here. What is x to the 7th divided by x to the 5th? X to the 2nd. Then we have x to the negative 6th divided by x to the 9th. Perfect, x to the negative 15. Now technically we should keep going with that. What is x to the 2nd times x to the negative 15th? Good, it's 2 plus negative 15 is negative 13. Now on the bottom, we have some work to do. We see another fraction bar, so we have to do what's on top of that one first. What is x to the 8th times x to the negative 11th? X to the negative 3. And of course, we still have the x to the 5th on bottom. Now we'll divide x to the negative 3rd divided by x to the 5th. X to the negative 8th, good. And finally, x to the negative 13th divided by x to the negative 8. X to the negative 5. Perfect. Negative 13 minus the negative 8 becomes negative 13 plus 8.
On that last one on the top, you can't cross multiply there. You have to do them.
That's times, not equals. That's a very good question. The symbol here is times. So if it were equals, we could cross multiply. But since it's times, we can't. Now you could cross cancel. But cross canceling is only necessary if it's going to stay a fraction. Since we can actually reduce the x to the 7th over x to the 5th down to a single item, the x squared, it's easiest to do that rather than trying to cross cancel between our multiplying the fractions. So let's take x to the 5th times x to the 4th over x to the 19th over x to the negative 8th times x to the negative 11th over x to the 3rd. All to the power of negative 4. Told you I had to make it worse.
Almost tempted to take the sharp stick over this one.
Hang in there. So now on this top one up here, the first thing we have to do is we're going to have to reduce that fraction. So the x to the 5th isn't going to change. What is the x to the 4th divided by x to the 19th? Negative 15. Perfect. Now I sometimes get asked, well, isn't this multiplication and then division, and don't they happen at the same time? They do normally. If it was written out as x to the 5th times x to the 4th divided by x to the 19th, then we would go left to right on it. But since it's with the fraction bar, that fraction bar implies that division has to happen before the multiplication. To keep going on top there, what is then the x to the 5th times x to the negative 15th? X to the negative 10. Very good. On bottom, what do we have to do first down there?
Multiply the top.
Multiply the top. X to the negative 8th times x to the negative 11th. X to the negative 19. And of course, that is still divided by x to the 3rd. Giving us?
So negative 22.
Perfect, negative 22. 2 more steps left. So we still have the x to the negative 10th divided by x to the negative 22.
X to the 12th.
X to the positive 12. Good. Negative 10 minus negative 22 becomes negative 10 plus 22, which is positive 12. And of course, we still have to the power of negative 4. Perfect. X to the negative 48. Great. I think it's time to let you guys try a couple of these in your notes by yourself. I'll try to be sort of nice. Give that one a shot. I'll give you a minute and a half or so to work on that. See a couple of you still writing, but let's go ahead and see how you're doing on it. What's the first thing we have to do? We have to combine the x to the 7th times x to the negative 13th, which is x to the negative 6th. Good. Then we have to combine the x to the negative 5th times x to the 9th, which is x to the positive 4. Very good. Now to keep going on top, the next thing, we've got to divide that out. What are we going to get? X to the negative 10. Good. Now I get asked all the time, well, couldn't I just do the next step on the bottom next? I could, but it's technically you're not supposed to be jumping back and forth. You're supposed to do everything on top first and then everything on bottom. That's why I leave it open. I don't rewrite it at least, so I don't have to worry about it. But then I'll go back. Now I'll work with the bottom since the top is down to a single exponent. On bottom, what do we have to do first? Ten to the 8th divided by 10 to the 13th is, or not 10 to the 8th, x to the 8th divided by x to the 13th is x to the negative 5th. And then x to the negative 15th divided by x to the negative 21st. X to the 16th. Good. Now on the bottom, we have to multiply those. X to the negative 5th times x to the 16th is x to the 11th. Perfect. Now we've reduced the top to a single number. We've reduced the bottom to a single number. We can go ahead and divide. What is x to the negative 10th divided by x to the 11th?
X to the negative 21.
X to the negative 21st. Good. And that's all to the power of negative 5 to give us x to the 105th power. Very good. Any questions on that? I know those aren't really happy problems, but they're not so bad. Let's throw in a second variable. And I'm going to actually throw into this express using positive powers or positive exponents. Now looking up here, we have that fraction bar. Is there anything we can do on top? The x to the 8th times y to the 5th. Is there anything I can combine there? Say no. No, we can't, right? There's nothing to do there. Is there anything we can do on the bottom of that fraction bar? No. X to the 3rd times y to the negative 8th can't be combined. So we go straight to the division. X to the 8th divided by x to the 3rd is x to the 5th. Y to the 5th divided by y to the negative 8th? Y to the 13th. Now we do the power of negative 3. What do we get? Perfect. X to the 5th to the power of negative 3. 5 times negative 3 gives us negative 15. So x to the negative 15th. Y to the 13th to the power of negative 3. 13 times negative 3 is negative 39. So we get y to the negative 39th. Are we done? No. We need to express those as positive powers. How do we do that? We express it as a fraction. So it's x to the negative 15th, y to the negative 39th over 1. How do I make those powers positive? Yeah, we move it to the bottom. The x to the negative 15th, we move it from numerator to denominator or denominator to numerator. X to the negative 15th moves to the bottom, becomes x to the positive 15th. Y to the negative 39th moves to the bottom, become y to the 39th. Now there's nothing left on top, but we still have to have a numerator, so we put a 1 in there. Any questions? So we might have x to the 7th, y to the negative 8th over x to the 4th, y to the 5th to the power of 5. What am I going to do first here? Divide the x's. What do I get? X to the 3rd. What's next? Divide the y's to get y to the negative 13. Good. Next we have that power of 5. What's that going to give us? Perfect. X to the 15th. 3 times 5 is 15. And then negative 13 times 5 is negative 65. So y to the negative 65th. Of course, to finish that off, we make it a fraction. And it's going to become what? X to the 15th over y to the 65th. Good. So this one here is a little bit more complex. On top. Now we see those parentheses up there. Is there anything we can do inside either set of parentheses there? No. So we're going to combine. X to the 7th, y to the 5th, times x to the negative 13th, y to the 3rd is going to give us what? X to the negative 6, y to the 8th. Very good. We're adding powers. 7 plus negative 13 is negative 6. 5 plus 3 is 8. On bottom, z to the 5th times z to the negative 12th. Z to the negative 7th. Good. Now we have that power of negative 2. We can do each piece. X to the negative 6th to the power of negative 2 is x to the positive 12. Good. Y to the 8th to the power of negative 2? Negative 16. Z to the negative 7th to the power of negative 2? Z to the 14. Perfect. What's our last step here? Move the y to the bottom. So x to the 12th on bottom. To put them in alphabetical order, we'll put y to the 16th first, z to the 14th. A, B, C, D, E, F, G. Yep. Let's do one similar to that. Let's do this one. Actually, you know what? I'm going to have you try that in your notes. What's that?
Is that a negative, the second parentheses on the bottom, is that a 9?
For which one?
19?
Oh, that's a,
This
gotcha.
Y,
Negative 15. There we go.
oh, 5, okay.
I'll give you a couple minutes to work on that. So our first step, we're going to combine the top of that. X to the 8th times x to the negative 13th is x to the negative 5th. Good. On bottom, we're going to multiply the y to the 5th, z to the negative 4th, times y to the negative 15th, z to the 6th. What do we get? Y to the negative 10th and z to the 2nd. Good. Now we're going to apply that power of negative 5. What do we end up with on top here? X to the 25th. And on bottom? Perfect. Negative 10 times negative 5 is positive 50, so y to the 50th, z to the negative 10th. What do we have to do to adjust it? Move that z is in the bottom, we're going to move it to the top. So x to the 25th stays there, followed by z to the 10th, and the y to the 50th is positive, so it stays on bottom. Any questions there?
So really though, that those are the same, it's just they don't like negatives in the exponents?
Yeah, this is equivalent to this. This is just considered more proper grammar.
Okay.
There are, yes, grammatical rules, exactly. Like, don't end with a preposition and all that happy stuff, right?
Yeah.
There are a lot of things, actually, we run into in the next, probably more so in Unit 3, where the whole math practice is based on a grammatical type of thing. Realistically, what's happening is we're trying to make the calculation easier to do by hand. That's what most of the math grammar is based on, is hand calculations and making it simpler to do. Well, we don't do calculations by hand anymore, So a lot of that math grammar stuff is slightly obsolete. We still hold to it just because it's tradition. But I'm not on a test, unless the question specifically asks or specifically instructs to give your answer with positive powers, I wouldn't mark it wrong if you left a negative exponent there, negative power. But in my math lab, there are going to be questions where that is the point of the question, is express your answer with positive exponents. So one last thing I want to show you here. We saw those powers of 10, and we saw that the power, when it's a power of 10, really describes how many zeros. So 10 to the 7th is 1 with 7 zeros after it. 7 tens multiplied together is 10 million. There's another place where we have seen those powers of 10. It seems like we always come back to place value, because place value is just an incredibly important part of math that often doesn't get the recognition it deserves. In our place values, of course, this first place value was the ones, right? Second was the tens. What was this next one? Hundreds, then 1,000, perfect, 10,000, and so on. We might recognize this as being 10 to the 1. This is 10 squared, 10 to the 3rd. 10,000 is 10 to the 4th. 100,000 is actually 10 to the 5th. 10 to the 6th is a million, and we can keep going. Down here, the pattern actually fits, because anything to the power of 0 is 1. So 10 to the 0 is our ones place. If we keep going, 10 to the negative 1 is 1/10. 10 to the negative 2 is the hundredths, or 1/100th. So those place values are even consistent. This is why when they say that we have a base 10 number system, the name decimal number system implies base 10. That's what it means, is our place values are powers of 10. We've expressed large numbers like 7,800,000 in a lot of ways, and we try to shorten them. For example, we might express that as 7.8 million as a means of shortening it. But there's an alternative to writing out that place value of million. We could just write 7.8 times 10 to the 6th. You might recognize that as being our scientific notation. And scientific notation actually does come from exactly that, is naming the place value. What we do in scientific notation is we take that first digit, technically it's the first non-zero digit, and we focus on it. So we move our decimal point so that it's after that first non-zero digit. That's why it became after the 7. And then we name the place value of that digit. It was in the millions, or the 10 to the 6th place. So if I have like 0.00029, my first non-zero digit there is the 2. So I'm going to move my decimal point so it's after the 2. So 2.9 is what that becomes. The place value that the 2 is in is 10 to the negative 4th. That is what our scientific notation is telling us. That's what it means. Now, obviously, we don't want to have to write out our place values like this every time we convert numbers in and out of scientific notation. So our shortcut, if we look at this 7,800,000 here, the decimal point started here and it moved to here. It moved 1, 2, 3, 4, 5, 6 spots. Notice 10 to the 6th. That was a large number. large numbers have place values with positive powers of 10. So we know that that is 10 to the positive 6. Our 29 hundred thousandths are 0.00029. In that number, the decimal point started here and moved to there. It moved 1, 2, 3, 4 spots. That was a very, very small number. Small numbers have place values that are negative powers of 10. So it moved 4 spots, it's 10 to the negative 4. So if I have 0.0000083. First of all, that's going to become 8.3. 8 is my first non-zero digit, so everything's focused around that. I'm going to put the decimal point after the 8. Times 10 to the negative 7. Good. The decimal point had to move 1, 2, 3, 4, 5, 6, 7 spots. And that's a really small number. It is in the place values with negative powers of 10. So that is 10 to the negative 7th. We might have 490 million. So our first non-zero digit here is the 4, so we're going to focus on that and move our decimal point after it. That's going to become 4.9 times 10 to the 8th. Good. Our decimal point started here. When there isn't a decimal written, it's at the end of the number. Moved 1, 2, 3, 4, 5, 6, 7, 8. And 490 million was a large number. It was in the place values that have positive powers of 10. So 10 to the positive 8. So a quick conversion. $7,200,000,000 and 0.000000013. Convert each of those into scientific notation in your notes. So the first one, that first non-zero digit's there, so our decimal point's going to go there. Started here, so it's going to be 7.2 times 10 to the, and move 9 spots, and that's a large number, so it's a positive 9. Good. Over here, our first non-zero digit is the 1, so that becomes 1.3 times 10 to the, careful, negative 8. Good. It's a very small number, so it's a negative powered place value. 1, 2, 3, 4, 5, 6, 7, 8 to get there. Going the other direction is just as simple. We have 5.2 times 10 to the negative 6. We're going to take our 5.2. That 6 in the exponent tells us the decimal point has to go 6 places. The negative tells us that it's making this number smaller. Negative powers of 10 are very small place values. So we're going to move this 6 spots to make it smaller. So we go 1. To go any further, we got to add zeros. So 2, 3, 4, 5, 6. That's where that decimal point goes. So I would write that out as 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros. 5, 2. Put a 0 in front of the decimal point just for clarity. Or we might have 3.9 times 10 to the 5th. Same thing, we take that 3.9. The 5 tells us we have to move 5 decimal places. Is this number going to get bigger or smaller? Bigger. It's a positive exponent, positive power. So we're going to make it bigger. So we're going to go to the right one spot. To go again, we got to add a 0. So that's 2, 3, 4, 5. So that's going to be 390,000. Have you try a couple in your notes? So we're going to take these in scientific notation. 4.7 times 10 to the 7th and 3.8 times 10 to the negative 6, and put them in decimal or standard notation. So 4.7 times 10 to the 7th. Is that going to get larger or smaller? It's a positive power of 10, so it gets larger. Power is 7, so we go 7 places. So here's our decimal point. We go 1. We have to add a 0 to go 2, 3, 4, 5, 6, 7. So that is 47 million. $3.8 times 10 to the negative 6. Does that get larger or smaller? Smaller by 6 place values. So that's going to move 1. Then we got to add 0, 2, 3, 4, 5, 6. My decimal point goes there. So 0.0000038 is that in standard or decimal notation. A little note since we're at this point. Many textbooks, a lot of technical writing are going away from using the commas for the thousands and millions separator. The reason for that is in a lot of foreign countries, they use a comma for a decimal point. If you see 2, 3, 1, that is not a misprint. Oops. That is actually what we would call 2.31. They use the comma instead of a decimal point. I'm not sure why they use a comma, but they do. So in order to avoid confusion on something like 4,281, is that 4.281 or 4,281? What they do is this. They just use an extra space. So it's an extra half space technically, 4,281, instead of using the comma. So the 47 million would just be written 47 with an extra half space, 3 zeros, and another extra half space, and another 3 zeros. Like that. So you can see that extra little half of a space there. Writing out by hand, it's hard to do. They carry that pattern through then after the decimal point here. It would be awkward to try to put commas in there because we've never done that. But we can keep that same spacing like I did. Every 3 places have then that extra half space. It just helps us keep track then of the decimals. So just something to be aware of that you may see. If you ever work for a company that does business internationally, you may see that notation of 2, 3, 1. That really is just 2 31/100ths, or 2.31. Okay, we're down to our last few minutes. Does anybody have any questions? Okay, so as I promised, I will have your tests to you by class tomorrow. I'm going to send them to your WITC email address. So as I mentioned, if you want it sent to a different email, send me a message from that email account, and I'll just respond to your message with a copy of your test. For now, homework 6A covers the material today. Because of the test yesterday, we'll only have 6A and 6B for this week. There's only 2 homeworks this week. So I'd recommend you get started on that, and we'll see you all tomorrow.